Hello and welcome to Friday's edition of Cracking the Cryptic, where I'm going to be having a look at a puzzle by two galactic-sized brains. Marty Sears and Dorlir, the maths professor, have combined to construct Galaxies Collide, which has an intriguing rule set, and if I may say, very few clues in the grid. And this is what I'm going to be having a go at today. Apparently this is just wonderful, and I'm looking forward to it, but with some trepidation. I've selected a more difficult puzzle than I was planning on doing today, and that is because I have rather more time than I was envisaging I was going to have. Those of you who are aficionados of the channel will know that today I was meant to be playing golf, which was why I was meant to be not doing the crossword video, and Mark indeed stepped into the breach this morning to do the Times Masterclass video that normally I would do on a Friday morning. But because my golf has been cancelled due to the inclement weather, I did have a chance actually to record myself solving today's time. So if you want to watch me do the same puzzle that Mark did, then I've put that video over on Patreon for those of you who follow us there. Obviously, thank you so much if you do support us there. You keep the channel going, literally. But anyway, the other corollary of that, and me having time to do a crossword video, is that I also have time, or more time than I thought I was going to have, to do today's main video. So I've selected from a slightly harder difficulty bracket. The testers divide the puzzles they pass into difficulties, so that Mark and I can try and plan our days appropriately. So I've gone up the difficulty scale. It feels, when it goes beyond a week since you've solved a Marty Sears puzzle, that feels far too long. So Marty Sears and Dorlir, this is what I'm going to have a go at. We'll see how I get on. Now, other news. I've mentioned the crossword thing, which is one of the things I wanted to talk about. Oh yeah, I hope you don't mind. I'm going to go on another little excursion. I'm finding out recently that rather more friends than I'd expected of mine do actually watch the channel, at least occasionally, which I find completely disconcerting. But one of them, I was sort of talking about and asking why he enjoyed it, and he said it was sort of the antidote to the internet, in the sense that he finds his interactions with the internet, they do a number of things. They raise his blood pressure, they make him angry, and they shorten his attention span. That's how he describes his average interaction with things on the internet. And he says that the channel does sort of the opposite of that. It expects him to have a longer attention span. It doesn't make him angry, except when I miss digits that I should get. He says that is a cause for concern. But basically, it's in some ways cathartic. And yeah, he was saying that he wouldn't be surprised if we were followed by quite a lot of people who didn't really like puzzles, but just like the experience, just like the peacefulness of it, which I thought was intriguing. Anyway, Will, I'm talking about you. Thank you for your wise words, and I wondered what the rest of you made of them. Now, what else? Oh yes, I mentioned this yesterday, but the Stratford Literary Festival, which is actually held in Stratford upon Avon, is coming up, and Mark and I are doing a live edition of Cracking the Cryptic on the 27th of October in the morning at 10 a.m. Here it is. Now, I had understood a week or so ago that had sold out, so I'd stopped mentioning it. But what they've actually done is they've moved. They have a couple of different venues they can use at the literary festival, so they've moved us into a bigger venue. It's not quite Taylor Swift-esque, but we have, we're going up in the world. So if you did miss out, there are now a few more tickets. There aren't loads more, but the venue is only slightly bigger. But it does mean we should be able to accommodate more people. So if you are interested, we'd love to see you. We're so looking forward to actually meeting real people, because although we have these conversations, sometimes to thousands, sometimes to hundreds of thousands of people, it's one way in a sense. So actually meeting real people who do watch the channel is fantastic for us, and we're really looking forward to it. So that is, we can see there, it's on the 27th of October, and hopefully we'll meet some of you there. Now, over on Patreon, we have also released now all of the solution videos to the September monthly competition. So if you were stuck on any of those puzzles, there should be help available now. And a quick plug for what we've got coming up on the 1st of October, which is the Skunk Works. No, it's not the Skunk Works, Simon. What are you talking about? It's the Paint by Numbers Institute. Misspoke. Sorry, Paint by Numbers Institute. And these wonderful Japanese sums puzzles, where the great thing is that at the end of the puzzle, you get a picture. You can see it's called Caroline's Halloween Adventure. And the puzzles in this are definitely more approachable than September's were. So if you did get stuck on September's and found them a bit hard, you should be definitely okay to make your way through next month's reward. So look out for that. That's coming on the 1st of October at 4 p.m. UK time. And birthdays. Let's do a birthday. One birthday for today. Aaron, you've turned a number that was the answer to Life, the Universe and Everything, for those of you who follow Douglas Adams. I know this because your wife Liz wrote to us and said you might appreciate a shout out. So Aaron, I hope you have a brilliant birthday today, with of course large amounts of chocolate cake. And then I've got 2 apology birthdays to do. I am so sorry. I got so caught up yesterday in the Peddling Pianists' parents' anniversary that I forgot to do the actual birthdays from yesterday, and I've let down Kinley, whose brother Cole wrote to us in plenty of time. This is totally my fault. I'm so sorry, Kinley. I know that you're a student pilot. You're not Maverick, are you? Kinley, I can trust that you're not Maverick. Student pilots, that worries me. But anyway, Kinley, I do hope you had a great birthday yesterday, with of course a large amount of chocolate cake. And then Martin, it was your birthday yesterday as well. I'm so sorry I didn't say it yesterday. You turned 53, and I know this because your partner Diana wrote to us. And I know, Martin, that you do follow the channel quite religiously. You watch my videos in the evening, and then with your coffee the following morning, you watch Mark's video. So thank you for being such a supporter of the channel. And Diana, I hope that the cake making went well. I know you're not a professional baker, but you have every chance to put a 3 in the corner with Martin reaching 53. So many happy returns. I hope the chocolate cake was good. And with that said and done, let us turn our attention to Galaxies Collide by Marty Sears and Dorlir. So I am literally wrestling today with, I would guess, could be higher, but 360's worth of IQ from the 2 of them. It's probably not far off that, and it might be higher than that. I mean, that's quite daunting. Anyway, these are the rules. Normal Sudoku rules apply. So we've got to put the digits 1 to 9 once each in every row, every column, and every 3x3 box. Divide the grid into 2 galaxies. Every cell in the grid belongs to one of the 2 galaxies. Each galaxy must consist of a region of orthogonally connected cells and must have 180-degree rotational symmetry. The central point the central point around which a galaxy is symmetrical doesn't need to actually belong to that galaxy. Okay, I'm going to carry on reading the rules, and then I'm going to try and understand them. No 2x2 area may belong entirely to one galaxy. One of the galaxies behaves like a German whisper, i.e. orthogonally adjacent cells in this galaxy must have a difference of at least 5, and an arrow cell counts how many cells in its own galaxy are being pointed at altogether by its arrows, and this combined total is displayed on the arrow cell. The arrow cell itself is not included in the count, and vision is not obscured by the other galaxy's cells. There's a lot there. There is a lot there. Let me go back, because where my mind went immediately was that this is some sort of spiral galaxies puzzle. What is a spiral galaxy? A spiral galaxy is a galaxy where you have to sort of define. Let's put a red thing in there. So if this was the center of a galaxy, then that galaxy has to have rotational symmetry around 180 degrees. So that means if we spin the shape of the galaxy around 180 degrees, if we turn it 180 degrees, it should look the same. So if those squares were in the galaxy, then the galaxy would have to have these three squares as well. And then if we added this square to the galaxy, that square would be in the galaxy as well. So you have to keep the shape having its rotational symmetry. Now, the other thing... Oh, I pressed the wrong button, but it works the same. The other thing I was going to say, as I was reading the rules, is that there's a lot of yin-yanginess. Yin-yanginess. There's a lot of yin-yanginess about this puzzle, because we can't have any 2x2 areas that are just in one galaxy, which is typically a yin-yang rule. And we can't have... Well, we've got to divide the grid into two areas, which is the same as yin-yang, and those regions are orthogonally connected. So this won't work, probably. I don't think this area is rotationally symmetrical about 180 degrees, but let's talk about how, that sort of pattern there obeys all of the rules of this puzzle except the one that says that the purple has to have 180 degree symmetry and the green has to have 180 degree symmetry. Yeah, they definitely don't. They definitely don't. But just to explain why it might be worth just taking a quick look at this, you can see that all of the purple squares form an orthogonally connected region. Orthogonally connected means connected across an edge. So if you added that one into purple, purple is no longer orthogonally connected and therefore wouldn't obey the rules, because this square only touches the rest of purple at a point, not an orthogonal. It's not an orthogonal connection. But there's no 2x2s of greens, there's no 2x2s of purples anywhere in that grid. So that is the bones of what we have to do, except that when we draw them, we've got to make sure those two coloured regions have 180 degree symmetry in this puzzle. And then one of those regions has to behave like a German whisper. So let's go back to our original. Let's imagine this was a German whisper, and this was a 1. Then this square here would have to be at least 5 different from 1. So it would have to be 6, 7, 8 or 9. Right, so that's that part of the rules. Now there was another bit which was to do with the arrows, wasn't there? So how do the arrows work? So the arrows... So this square... Oh, but does that has to be in its own region, doesn't it? So we look at this region, give it a colour. We count how many purples there are in all 3 of those directions, and we write that number in there, is I think what we have to do. So it counts how many cells in its own galaxy are being pointed at altogether by its arrows. Yeah, that is what we have to do. Do have a go. The way to play is to click the link under the video as usual. But now, I get to play. Let's get cracking. Now, how are we going to get cracking? Do we start by... Do we start with the arrows? I'm not sure. I'm not sure how much we'll be able to do yin-yang wise, but we can... That digit is only got 1 arrow, that's only got 1 arrow, but that sees quite a lot of cells, doesn't it? So that sees 7 cells, so that could be any number up to 7. That only sees 5 cells, so that could be any number up to 5. Okay, no, this isn't how to do it. It's not the arrows. We need to do something. We need to do something with this yin yang. So let's do some yin yang principles quickly. You can't have checkerboards in yin yang. So we're not going to be able to build galaxies that have this sort of feature anywhere within them. And that's because of this orthogonal connection requirement. So because we have to connect the purples orthogonally, however we choose to do that and whichever direction we go to do it, what will happen when we achieve purple connectivity is that blue connectivity will then be impossible. We can't connect these orthogonally anymore because you're going to create a pool of purple around the blue in one of the two directions. So that is one principle we're going to need to obey in building our galaxies. It's quite interesting actually, isn't it? Because we're going to have to we're going to have to do this with yin yang, and the thing that that's jarring slightly in my brain is how we're going to preserve yin yang principles but also achieve the symmetry. But anyway, let's also deal with the perimeter, because there is a point in yin yang that comes from that checkerboard logic that applies in the perimeter. Let us make the perimeter all one colour. That's fine. That is possible. But let's now introduce a second colour in the perimeter, like this. Now, here's the question. This is also still fine. But could we have another change of colour in the perimeter? So let's say, could we make this square anything other than purple? No is the answer. And it's similar logic to the checkerboard. We have to connect these green regions together now. And again, it doesn't matter how we do it. And it doesn't matter if it's rotationally symmetrical when we've done it. But that is going to break the puzzle. Because now purple can't connect to purple, because there is a wall of green that's introduced. So the perimeter of a yin-yang puzzle can change colour once. So that might be how we're meant to start this, because if we look at this congregation of cells up here, they can't all be one colour, can they? In fact, I'm probably going to use blue and orange today, because blue and orange are our most colourblind friendly colours. And I need two colours only, don't I? So this can't all be blue. So something up. So this is two colours. But the same is true down there. That's got to also be two colours. So let's just make that corner blue for a moment. Does that have to be blue? Or does it have to be orange? Or could it be either? There has to be a blue down here somewhere. And that blue means the centre of rotation for any shape that joins this cell, say, to that cell, has to be somewhere near the centre of the grid, doesn't it? Well, it can't be here, for example. That will not work. I feel like it must be in box 5 and towards this side of box 5. Well, frankly, I want to put it in the middle. But why does it have to go in the middle? The middle? Okay, hang on. No, let's do this a different way altogether. What colour is the middle? I don't know. I'm going to deem it to be blue. This is okay. now you can't put blue in the perimeter of the puzzle. Is that right? That feels right. If the middle is blue, how could you put blue in the perimeter? How could that be blue? If that's blue, it's rotational. Its rotational counterpart would be here. No, here. And however I join this up, well, it would have to be rotationally symmetrical. I don't know if that is I probably messed that up. I think I have messed that up, haven't I? I tried to make something rotationally symmetrical and failed. That might be correct. But however I join it up, I've made a wall across the grid. I can't make walls across the grid. Because if I do, there can't be any orange on both sides of this line, and there must be. I mean, you can't fill all this with blue because we can't have any 2x2 in the grid not having orange in it. So, you know, there's going to be orange over here, there's going to be orange over there, and those oranges can't connect. Now, the only thing that makes me hesitate for a moment about that is it necessarily the case that if I make this blue and I put blue in the perimeter, that this is the centre of rotation of that region? That's not necessarily the case, is it? I mean, if, for example, we did that, then this could be the centre of rotation of blue, and blue only looked like this. But that's clearly nonsense. The reason that's clearly nonsense is that if the centre of rotation of blue is not in this row, then this shape would never go down to the bottom of the grid at all. It can't, because it can't go out of the top of the grid. So if the centre of I think this is valid. This doesn't work because now all of this would be orange. Blue can't get down here. So if you whatever the middle of the grid is, the implication is that if you put blue anywhere in the perimeter, yeah, I mean you can do silly things. It still doesn't work. You could have this as the centre of rotation for this shape, but the point there is still the same. You're still making a wall. It's just this isn't the centre of rotation. So I think what I'm concluding is that if the middle is blue, any blue you put in the perimeter at all has to have a centre of rotation that is in this. So if the blue is in this row, the centre of rotation has to be in row 5, which means there is blue on the other side of the grid, and in connecting that blue together, you will create a problem. So I think that the middle of the grid... Well, yeah, okay, so the point there that we're reaching is that whatever the middle of the grid is, I've called it blue, all of the perimeter has to not be blue and has to be orange, and then these have to be blue to avoid a 2x2. That is absolutely weird. That is a very, very strange deduction. But surely that's very important. That's definitely right, isn't it? Whatever I make the middle, if I put that colour on the perimeter, I know that there must be blue. Yeah, I'm just thinking about whether I can state it in a more precise way, and I don't think I can do much better than I've done. If I make that blue, we know that there must be. If the centre of rotation of this is not in this row and is any higher, it can't be lower because that's going to take us off the edge of the grid when we rotate around it. This square would have its rotation off the other side of the grid. If it's any higher, you're going to get a 2 by 2 of orange in here. So the centre of rotation does require that this is going to reflect onto the other side of the grid. That is going to create a wall across the grid somewhere, somehow. And that is going to prevent any orange to the left side of the wall meeting any orange to the right side of the wall. And there must be orange on both sides of the wall because every 2 by 2 in the grid has to contain orange. I think it is right. I think it's right. So we can go back to, oh no, it won't let me now. Let's go back to here. I am convinced. And I can go back to here. And now, that has a maximum value of 4. Because it sees 2 different colours in its row. So it can't be 5. Hang on. Huge point. Orange is not capable of being whispered. Because we haven't really talked about this at all, but there are secrets of German whispers lines or German whispers relationships between cells. And let's imagine that we do try and make orange into a whispers sequence. We can see there must be a 5 in row 1. Let's put it there. What is the next digit in either direction? This digit has to be at least 5 different from 5. If we go down, we get to 0. That's not a Sudoku digit, and further negative is obviously bad as well. And if we go up, we get to 10, which is also not a Sudoku digit, and 11, 12 are also not Sudoku digits. So you cannot put 5 on a German whispers line, but because there must be a 5 in row 1, orange therefore cannot be 5. So blue is our whispers galaxy, and well, here is an interesting thought in that regard. Because there is this orthogonal connection across blue that's required, we're going to get this bishop's parity thing going on. Okay, so I need to explain some of this. So let's imagine these 3 squares are a German whispers relationship. The critical thing to realise, let's make this a lower digit than 5. In fact, let's actually literally do that. Let's do it like that. If this is lower than 5, we can say immediately that these 2 digits must both be higher than 5. And that's because even if this is a 1, and it only increases in value by the minimum amount, which is 5, these would still reach 6, wouldn't they? And they would be higher than 5. And then imagine we continued here. So let's make this a 9. What's this digit? Could this digit also be higher than 5? No, because if it's 6, 6 and 9 are not far enough apart. So this digit would also have to be lower than 5. And you can see we're getting this oscillation of the polarity along the line. Now the interesting thing about an orthogonally connected region that has this property of oscillation is, let's look at this square. Let's imagine this square was blue. How many steps would we take from this square to reach this square via an orthogonal connection? Now obviously the simplest way would be like that. And that's 2 steps. But even if we go a more complicated way, let's go that way, you're always going to take an even number of steps. 1, 2, 3, 4, 5, 6. So that means that whatever the polarity is of this, high or low, it's preserved for cells on the same bishop's colour. So that means that if we can discover, well, it's very likely this is going to be a high number, because we're counting, maybe it has to be a 9 actually, I hadn't thought about this, but if that's, let's say that that's high, higher than 5, then we could immediately write higher than 5 into all of those, because they are on the same bishop's colour. And when the galaxy eventually reaches this square from here, we will have gone an even number of cells. In fact, now I'm seeing it, the blue region this is the centre of rotation for both. This is the centre of rotation for both regions, isn't it? And that explains why there was that weird line in the instructions about the central point around which a galaxy is symmetrical doesn't need to actually belong to that galaxy. Because this doesn't belong to the orange galaxy, but it is the centre of rotation of the orange galaxy. Now, does this have to be 9? That would you can see it's only going in 3 directions, which looks jolly deliberate, doesn't it? But it would allow us, a 9 would cause that pattern. These would all. This would be. Oh no, hang on, that doesn't work. If that's high, that can't be high. Oh, okay, alright, this isn't 9. That's weird, actually. Because if this is 9, I have to make all 9 of those blue. And that by rotational symmetry, these 3 become blue. And this total is not, by Whisper's logic, we know this is meant to obey the Whisper's rule, so this should be a low digit, a lower than 5 digit. But it's obviously seeing 5 already, or 6 actually, in its column. So these would both be high. That doesn't work. That's awkward, isn't it? Because the moment I make this slightly smaller, things I could miss this digit out now. I could make that orange and make all of these and do that sort of pattern. And that would be rotationally symmetrical. And if this was orange, it would have a small count naturally, because it's seeing so much blue in its column. So that doesn't get restricted very much. Bobbins, okay. So maybe I've got to use the fact those 2 are the same polarity. That's always true, whether this is high or low. Yeah, there's got to be some blue here. Yeah, because my suspicion is this is a high number, because I've got so much real estate to occupy. So if this was high, it's counting how many blue cells it sees. Oh, hang on. Right, if that's high, it has to be a 6. That would be a 1. If this is high, because what I'm thinking is I think this is going to be high. which means by polarity logic this is high. But the only way this can be high is if all of those are blue, because it only sees 6 cells beneath it. So this would be a 6 and this would be a 1. Because 6 and 1 are monogamous along the whisper. If you see a 6 on a German whispers line, there is only one Sudoku digit that is 5 away at least from 6, and that is the digit 1. Oh, I see. Ah, no, that doesn't work. Right. Okay, this doesn't work. Because actually, now I've realised I can't make this one colour. Because I'm going to cause a monogamous problem. A monogamity problem? I don't know what the correct word is. But if all of that is blue, all of this is blue, forget these numbers, it's not relevant. If all of these are blue, by symmetry rotating around here, these are all blue. But what's that number? And the problem with this number is it's 6. That's what we learnt from this number. And you can't put 6 in the middle of a German whisper string because what are these 2 digits? Boom, they both have to be 1. So that's wrong. Right, and that's very pretty. That's a very pretty way of thinking about it then. So basically what it's not this, is what we're learning. It's this. This is telling us that the polarity of this digit is actually lower than 5. Because we're having to obey whispers rules, so it can't be 5 in this square. We've proved it can't be 6 because of what happens over here. So it has to be low, which means that this is low, this is low, this is low, and this is low. And we can immediately do that. So this is orange, because if this was, if it's blue, it's got the wrong polarity. So this, but the rotational symmetry of orange is the middle, so that's orange, and that means that blue, in order to grow, must grow in both directions, because the moment you extend it in one direction by rotational symmetry around this square, you have to rotate it in both. And now that digit is high by whispers logic. This digit can't be 6, because if it's 6, again, you're going to force this to be 1. But we know that this is not the full extension of blue. Let's call it that. If blue stopped there and we ringed this with orange, you can see the blues aren't connected. So this is extending, and wherever it extends, it's going to extend here, here, or here, or all of them. And the moment it extends, that's going to result, if this is a 6, there's going to be a 1 here, here, or here, or all of them. And if there's a 1 here, that's not possible, because any extension will break, will get us a repeated 1. Similarly, this can't be a 4, because if this is a 4, it's going to be surrounded by double 9. So this digit is very small, actually. So there's hardly any... I was about to say there's hardly any, but... So we have seen 1 in the northerly direction, 1 blue, I mean. And if this is 3, this will be an 8-9 pair. And then that will be seeing lots of blue. But yeah, that's not surprising at all, because it's picking up so many different directions of bluishness. This can't be 1. If that's 1, all of those are orange, because we've already seen the 1 blue, and they can't all be orange without creating 2 by 2 problems. You need quite some blue, actually, into that string, don't you? You need to deal with the 2 by 2. Oh. No, you only need 2 more. You need to deal with the 2 by 2 here. You need to deal with the 2 by 2 here, so that's 2 more blues at least. But you could deal with this one by putting that 2 by 2 by putting 1 here. So okay, so you only need 3 blues in this column, but you can't have 2. That doesn't work. This is 3 or 4. So the next digit, if this grows this way or this way, if that's 4, it can only grow one way, because 4 is monogamous with 9. So if that is 4, one of these is 9, but it only goes in one direction. So it's Harry Styles'd if it is a 4. Now, so this is, I mean, actually, just to pause for a moment, I could believe at this point that the clues that we've got yield a unique colouring of the grid. But it is pretty extraordinary that the clues that we've got don't only cause a unique colouring, but they cause all the digits within that colouring to be uniquely determined, especially when you consider that the orange digits don't do anything. The orange... Yeah, I mean, the orange digits have no inherent restriction on their value. I suppose that one does, because it's got an arrow on it, but most of the orange digits don't have any value. So all of the powerful digits are going to be blue digits. And there can't be that many blue digits in here. There's literally none in the perimeter. It's really, really weird. So what's that? If that's orange, then these two have to be blue to avoid a 2 by 2. And the maximum value of that orange would be 1, 2, 3. It would be a 2 or a 3, but yeah, again, that's actually a good illustration. If that's orange, I think that's 2 or 3, and I don't think we care which. I mean, it doesn't do anything. It makes those blue, I suppose. It would make this high and that high by bishop's colour, but there's no arrows in these squares. What about if this is blue then? If this is blue, then we don't even benefit from any 2 by 2s. All we know this is low, 1, 2, so it can only see a maximum of 2 more blues in the column. Oh, that digit isn't. I don't think that's where the magic's happening here. It might be that one. I don't think it's this one. I just think there's too much flexibility. It might be that one as well. Maybe I needed to think harder about that one. I'm going to try this one, and then I'm going to try that one. I haven't thought about this one, but that looks a terrifying one. I suppose whatever that is, that's the same colour as it, by symmetry around this point. So this is either double blue, which would be small. That nearly breaks straight away. Because if that's double blue, then all the low digits in the world have been used up, haven't they? In box 5, because these would be low by polarity. So all those would be from 1, 2, 3, 4. So this would be a very low number, and it's got so many arrows on it. That feels incredibly unlikely. But I don't know, actually. See, the problem is, it's a bit like a compass puzzle, in the sense that if you joined this up using that connection to its friends on the left, you'd pick up one more blue here, but you wouldn't have to have anything in the column. I mean, you might have to have something to avoid 2 by 2s. It's incredibly difficult well, it's quite difficult to see whether that results in a problem without doing a heavy bifurcation, which I'm reluctant to do. Okay, I'm going to come back to this one again. So this one is counting the number of blues in those squares and these squares, but it can't be bigger than 3, and it is 1 for this one at the moment. Now, it's going to be some connectivity nonsense, isn't it? So what I'm trying to envisage is how blue all connects in the grid. Maybe... No, you can. No, you can. I was thinking maybe there's a reason you have to have blue somewhere here and here. Because if all of those are orange... But it's fine, isn't it? This is providing the pathway, so we can connect these somehow. I don't know. We've got to be careful of 2 by 2. So we could have something like that. We could do an upside down fork at the bottom. What's wrong with that? I mean, there might be something wrong with that, but it's... Oh, I suppose no, that would break this square, which would need to have a low number in it and wouldn't. But in principle, if you see what I mean, there's nothing... I mean, there are many other shapes that are possible. It's very hard to see that you can't make those totally orange. If either of them... you can't make them both blue, because that will break that. Yeah, because we haven't got many digits to play with. Because if I make them both blue, because of the rotational symmetry, these would both be blue. And then I'm up to 5 as this count, which is wrong. So in fact, I can have a maximum of 1 blue. I can have 1 blue. If I put 1 blue there, I get 1 blue there. And then I wouldn't be allowed. Those would both be orange because we'd have reached our count of 3. So say 2 blues here. And then all of this would be orange. Right, that doesn't work. Okay, good grief, that's very hard. That's really hard to see. Okay, right, so what we need to do is to look at this row very, very carefully. What happens if we put... We've worked out... Yeah, I think I've now worked out these are all orange. We've worked out you can't put 2 blues here because the count of this gets too high. If you put 1 blue here, let's just put it there, it doesn't matter which way it goes. The other one will be the orange. That's the implication if you make one of these blue. But the point there is that you get the same on the other side of the grid. But what digit do you put in here now? Well, it sees 3 already, and it can't be bigger than 3, so it is 3. And what's this digit? 1, 2, 3. It's the same number. And it wouldn't matter, obviously. It makes exactly the same if we made that blue and that orange. That would still have a count of 3, and so would that. So this is wrong. So that means... Let's go all the way back. Well, it actually doesn't mean this isn't 3, because we could have 3 vertical. But it does mean that there is no blue at all in that domino, which means there is no blue at all in the opposite domino. And now these squares are all blue by dint of 2 by 2 logic, and that has turned blue. Oh, it's so... I thought I was going to get that one, but no. Hang on, so what's this one? This is now seeing 3. We can do bishop's logic, though. We know this is a low number. So it's 3 or 4. Because it's on the same bishop's colour as this one. So it sees 3, but one of these could make it a 4 if either of these was blue. Golly gosh, it's tricky actually. It's very tricky, this. It really is. Does this now have to be orange? If that's blue, is it going to get too high? Or not? Because it sees that one. I think we're in the same position we were, actually. It sees 2. Actually, I'm not sure. I am going to give this a bit more thought. If this is blue, that's blue by symmetry. Now, I can disprove this. I can disprove this. Right, this is wrong. Sorry, but this is wrong. Because now let's do a very careful audit of how many blue cells this sees. Now, on the face of it, it only sees 2. But one of those must be blue, otherwise that's a 2 by 2. So that takes us up to a count of 3 blues, definitely seen by this. But how many blues does it see up here? And the answer is some number of blues. If all of those are orange, these 2 blues are disconnected. So now I'm up to 4 blues. Now if that's 4, that's 9. I could extend down. I thought I could break it. I thought it was going to be very difficult for this to be a 4. Maybe one of these has to be blue. If both of those were orange. No, because you can escape out the back door. Ah! No, don't know then. Okay, sorry. Still unsure about the world. What about if both of those are orange? Let's have a look at that. If both of these are orange, this is worse, because this is so worse because you get no restriction on orange for this being orange. The only restrictions on orange come in the sense there's no need for this to be low now or high. It can be anything it wants to be. Ah, but hang on, that's right. This is better. Okay, let's go for this digit. That is a 4. Because that is an orange that is arrowed. And now I'm going to come back here again. Because I'm very sure this can't be 3. I thought it couldn't be 4, but I know it can't be 3. If this is blue, it's low by polarity. So let's fill it in. 1, 2 or 3. It's seeing 2. One of those is blue to avoid this being a 2 by 2. And one of these is blue to avoid these being isolated from all their friends. That's 4. That's not able to be 4. So these are both orange. Alright, so what I am getting from that is that is blue and that is blue to avoid 2 by 2s. And the count of this is now... well, 1, 2... 3, 4. Okay, it's more than 4 because it can't be 4. So it's 5, 6, 7, 8, or 9. Okay. All right. But what we can do? This square is 6, 7, 8, or 9. The same logic. That can't be 6, can it? Isn't that going to give us the same problem with... Yeah, that can't be 6 because this will extend to one of those 2 squares. Anything on the same bishop's colour is high. So that's high. Can that be a 6? Maybe those two... If those were both blue, they wouldn't see each other by Sudoku. So... Here's something. I've got a 1, 2, 3, 4 quadruple in this column. Oh. So, how does that help me? I still don't know what this is, even though it looks like I do, because I've got 4 blues in the column. It's not counting itself. This is seeing 1, 2, 3, 4. But presumably, yeah, it's at least 7. So there's got to be more. Wait a minute. There's got to be more blues. I'm only on. This is only on a count of 4 at the moment. Oh, that's okay. That's brilliant. That is brilliant. That's my favourite. That, exactly that, is the most spectacular cell in this puzzle so far. Good grief. Right. Okay. This is not complete. It is not core 8 at the moment. We only see 4. So some number of blues have to be some number of more blues have to be included in specifically in those white squares to get to the total. They can't be included here because we haven't got any more space to put any more blue squares in. But what's going to happen when we put a blue there, say? Well, then we're going to have to put its counterpart here, aren't we? So any increment in blue from our count of 4 is in even steps, because if I make either of these blue, I make the equivalent down there blue. So this is even. It must be, we can't increase it by only 1 in these directions. So that is 8. And in fact, then, in order to get to 8, everything is blue. Right. So that is so clever. It is such a clever piece of setting. Right, look at this. Hang on. That is 3. It sees 3 vertically. So that can't be 7. 7 and 3 are not 5 apart. So that's 9. Hang on. Right, well, should we label up? Right, so this is 6 and 7. These are therefore 1 and 2. Because we can't put 4. 4 can only go next to 9 on a whisper. And one of these is 6. Yeah, that's gorgeous as well. Right. I don't know. From this column, I know one of these is 6, but I don't know which one. Let's imagine it's that one. If that's 6, what does it do to its surrounding environment? Well, firstly, it makes this digit 1 by Whisper's logic. Now, can either of its orthogonal neighbours be blue? No, because if either of these was blue, they would be the digit 1, and that would clash. So this 6 would force its orthogonal neighbours, its sort of westerly and easterly neighbours, to be orange. That's forced. Now, the point is that by symmetry then, those would be orange, wouldn't they? So actually, we don't give a monkeys which of these is 6 at this point. We just know one of them is, and one of them therefore will cause that pattern, which causes that pattern always. And now, these squares have to be blue to avoid 2 by 2s. This is a brilliant puzzle. I mean, I shouldn't expect anything different. Right, how do I get from this channel to here? I've got to go through there. And therefore I get a little robot hand appearing here. And a little robot hand, because by symmetry I must get a robot hand down here. I can obviously fill in loads of these digits now with highs. All of those are highs. And we can probably... Yeah, you can rule out 6 from there. So 6 from there, because that would cause double 1 in the same row. That can't be 6, it would cause double 1 in the same box. So the corollary of that is that one. This is a low digit, but that can't be 4 for the same reasons. This is a low digit and that can't be 4. Oh no, come on. We must be close to capturing what's going on now. What's that? 1, 2, 3, 4, 5, 6. It's at least 6. Oh yes, it's 7 actually. That is 7. Because I can't make both of those blue without creating a 2 by 2. 1, 2, 3, 4, 5, 6. Yeah, 7. And that 7 is caused by one of these being orange. So neither of these can be orange, and both of those are blue. By symmetry, both of these are blue, and that fixes that that one is the orange one to avoid a 2 by 2. Which means that one is an orange one. Yeah, it's just the same logic, isn't it? That's not 7. That's not 7. Oh, I see, and we get left with a sort of ambiguity in the sense that it's so are these the same number? Is that what we're really learning? I suppose that's always been true. From very early in the puzzle, these have been the same number. Because obviously this one's counting. If we made that blue, we're making that blue, so we're increasing the count of both by 1. Okay, so this is now, that's a 1 or a 2, because it's low and it's not 3, and it's not 4. So this is high, is 6, 7 or 9. It can't be 6. That would cause double. Oh, it can't be 7, this can't, because it's next to a 3 or a 4. That's a 9. So this isn't 9. That's going to do something to those in a minute. Let's just think about that in a second. Okay, let's come back over here. The maximum, also, you can put 1s next to 6s and 1s or 2s next to 7s. So these lose their 3s and their 4s. I've got a 1-2 pair. I've got a 1-2 pair. Come on, what on earth? It is remarkable. It's remarkable that this, I don't know, I'm going to have to label all these up as well, aren't I? There's that. Oh, yes, that one's the key one. That's high by polarity, but it can't be 6 because that would cause double 1, so that's 8, which means that's 6. That's weird. So 6 has to be next to 1. That fixes this. Oh, I see. Look. This is going to go through the grid because now 2 can't be next to 6. So that's 7. That's 6. This is so unbelievably brilliant in terms of its construction. This is 8. Oh, 8's not a great digit. 8 can't be next to 4 on a whisper. It can't be a 1 by Sudoku. 9 can be next to 4. Oh, bother. Right, so this digit is a 2. It sees all the other low digits. So that's a 1. So this is a 2. So that's got to be next to 7. So this isn't 2 or 1. This is 3 or 4. This can't be 2. This can't be 4 because it would be next to 8. So that is 3. So that's 4 and that's 1. And if that's 4, it's next to 9. That's one thing. But also, it's only seeing 3 blues, so it needs another blue. And that means that's blue, and then avoid a 2 by 2 by. So that's the shading. We've done the shading, and now all we have to do all we have to do is that the Sudoku that is, well, that's a 4 as well, because it must see the same number as that. We work that out. So that's 9. This isn't 1. This has got to be 7 or... No, it's a high digit. It's a 7 by Sudoku in the column. Can't be next to a 3. So that's a 2. That's a 3. Okay, and these are both high. And look. That's got to be 6, therefore. That has to be 7 or 8. It can't... No, it doesn't. It's got to... No, that's nonsense. It's 8 or 9. Sorry, I'm getting tired now. This is... It's because it's got to be 5 different from 3. Can we get this? Yeah, we can. We can get that one, but it doesn't give me that one. Or does it? No. Okay, what are those? 5s and 6s. So this row, 3s, 5s and 6s. Yes, where's 3 in that row? That's a good question. It's here. In fact, that's just straightforward Sudoku. All right, well, there's a 4 there by straightforward Sudoku. Okay, let's do straightforward Sudoku. I mean, it's outrageous being made to do Sudoku in Sudoku puzzles, but sometimes that seems to be what I'm forced to do. What about that digit? That's a 5. What about these digits? 2, 7, 8. That's a 2. What about this column? 3, 4, 5. That's interesting in the sense that it seems to have given me a 4, 5 pair in the bottom row. So that's not 4 then. That must be the 4. So this column? 1, 3, 5. I don't think that's quite going to resolve. No. Bobbins. Okay. What about... Don't know. I'm not going to get any more... Yeah, I'm not going to get any more help from the sort of arrows or the German whispers side of this, am I? I'm just going to have to do it. I am going to have to do it by Sudoku. Okay. Is there an easy way of doing that? 2, 4, 5, 9. Don't like... I was thinking about that row, but I don't like it very much. So I'm going to go and look somewhere else. What about this column? 5, 6, 7 and 8. No, that's not a sensible place to look. 5, 6, 7, 8, 9 into this column. It's weird, actually. I almost feel like I must have missed an implication because, well, it's exactly how I thought earlier. It's sort of... Oh, 2. It just doesn't feel like there's enough information, but that is a 2 by Sudoku, which seems to give me a 9 as well. That died a death very quickly, didn't it? There's a 2 down there, which means there's a 2 down there. Could it be 6? Could it be? Yes, okay, 6 has to be there by Sudoku. So one of these is a 6. Seven. Where is 7 in this column? It's got to be in that square, which actually isn't. It isn't the most brilliant deduction ever, but it is still true. So in this column, I need 1, 3, 4, 8. Right, that's naked. That can't be 1, 3, or 8, so that is 4. Which means that is 5, that is 4, that is 4. Okay, so we end up with a 3, 5 pair at the top of the grid. How many 4s have we put in? Many. Many, many, many. We can get all the 4s, like that. What about this row now? 2, 5, 9. Yeah, where's 5 in row 8? It can't be here. It can't be there. So it must be there. So that becomes 2. That becomes 2. That becomes 9. Which means this is 8. And oh yeah, that's great. Now we've done our entire blue region is finished. That's 9 in the corner. Feel like singing, but doesn't deserve it. This is a 1. Oh, this is a 1-3 pair. Okay, let's just see if we could. Yeah, we can. That's a 3 now. So this is 8, isn't it? This is 8. This is 7. That's 7 by Sudoku. These squares are 5 and 6, which is resolved. Oh, come on. This is now going, isn't it, a little bit? That's a 6. Oh, near. Oh, yeah. In fact, look. Let's just take a breath there. That's 6 and that's 6 by Sudoku. And that's 6 and that's 5. And I think all the 6s have just been completed. These are 1 and 8, which looks good from a Sudoku perspective, although I can't do it. These are 1, 5 and... oh, 1, 5, 9? So that seems to have to be 5. So that's 5, that's 5, that's 3. These two squares are 3 and 5, I think, which would put 8, 8, 1, 1, 7, 8, 3, I think. That is so ridiculously clever. Is it right? Yes. Wow. Wow. Marty Sears, Dorlir, you always deliver. You just deliver spectacular puzzles every single time. That is really brilliant. I do have to say, I do enjoy puzzles where there's sort of a meta consideration at the start. And I found it very interesting that you could sort of have to think about how galaxies might be able to be rotationally symmetrical in this puzzle. And even after you've done that, that was my favourite digit actually, which I thought was beautiful as an idea from a construction perspective, that this had its options of being 7, 8 and 9, but could only be even due to the geometry. Wasn't that brilliant? It's a brilliant puzzle. Thank you so much if you're still watching. Please do leave a comment for Marty and for Dorlir. They deserve all the plaudits in the world. That was absolutely brilliant. And we enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.